Here. Okay. This is you. Thanks, Philip.
Yeah, so hi everybody, my name is Philip and I am the COO of Ola, and I'm here today to give you a brief introduction to what we're building in case you have not heard of us before. We are basically a ZKVM team, or a CKVM team. We're looking to do both privacy and scaling. Oh, we had two screensavers here. So right, a brief background on scaling for Ethereum. There's been many different suggestions to how to do scaling, both horizontal and vertical. We've had different stacks with the OP stack and different CK stacks. And basically how we're different is that we're looking to do both scaling and privacy. If you wanted to, you could even use the Ola ecosystem as a standalone environment and run your own single dApp as a solo chain. One thing that we also, which is kind of out of context for this talk now, but we did look into the BitVM paper, which was kind of interesting, and we think, so BitVM, by the way, is a paper that was released 1 month ago in October of 2023, and it's about doing peer-to-peer in a two-party setting scaling for Bitcoin, which was kind of interesting, and we did look into applying our VM for that as well. So if you're interested, come to our booth and happy to discuss about scaling Bitcoin as well. So everything we've done so far is about making this as efficient as possible. There's many things, talking about Ethereum specifically, that aren't very CK friendly. And that ranges from different hash algorithms to how we can go about getting the trace, which is what's being proven at the end of the day, as small as possible. So we're running a RISC ISA. Our VM is fully Turing complete, so you can deploy any arbitrary logic on top of it, and gas would be the limitation in terms of what programs you can run. We also, as you can see here, have some CK-friendly hashes in Poseidon 2 and using Blake. So that's a little bit about the VM itself. This might be small here on screen, but basically the bread and butter of our solution is about achieving compliant privacy. And I'll talk more about that, but here is the technical overview. So how a full end-to-end transaction lifetime flow works in our system is that everything in the red here refers to client-side operations. So that would be the end-user device. And then we have our nodes here represented in blue. And at the end of the day, the L1 here could be Ethereum, it could be Celestia, it could be any chain. So whatever layer we deploy on, we just need a smart contract where we can send the proofs of the state changes happening in the Ola ecosystem. So just highlighting that this could be any layer. But we're looking to do this for Ethereum first. So in Ola, very similar to other privacy-oriented solutions, you would execute private functions at client side, so at your end-user device, meaning you send a partial proof relating to what transactions you've done, together with a signature. That's going to be verified on the node side, and the node would then continue with the rest of the public functions to be executed, and then we have some neat tips and tricks here using parallelization. There was some discussions earlier today about Starks versus Snarks. So our CK backend is based on Plonky 2, actually a modified Plonky 2 for recursion. And then we're using Starkey as our block builder. So fully Stark-based at the moment. We're using some parallelization here. It's kind of like a conquer and divide approach where you have specific operations, you divide them, and then using recursion, you prove them all the way up to the top. We also looked into using snarks. So you could use fflonk if you wanted to make the byte size smaller when you submit that to the layer 1. But then, as was mentioned previous in discussions today, you have some trade-offs. You're losing the quantum resistance, and you also have a trusted setup. But there's different ways to go about this. We have not launched our testnet yet. We're going to do that next month. So we'll see what we end up doing. Another thing is that we're using account abstraction. So if you're familiar with the Ethereum ecosystem, this is ERC 4337, if I'm not mistaken. So we're not looking to reinvent the wheel here, but we're not supporting EOAs in Ola. We think that smart contract accounts offer more flexibility to the end user, such as paying gas in whatever token you'd like. So we're looking to utilize the existing tech to make the platform as good as possible. Right. So privacy. This is actually the problem we're mainly looking to solve. And here we are kind of different to other actors in this space. So I'm sure most of you in the room are familiar with the protocol Tornado Cache, which has been a mixer on top of the Ethereum network. And the problem we've seen here is that when you have a complete black box, meaning you have no input whatsoever to what's happening and where the funds go, government and regulatory bodies have an issue with this. So what we've done in Ola is that we're looking to counter this with what we're calling partial native traceability. And I have a slide here showcasing some Merkle trees where we're going to go through how this works. So basically, to the far left here, we have the public tree. So Ola, if I didn't mention it before, it's a hybrid rollup. We're looking to support public and private smart contracts, and we leave this at the hands of the developer. So the developer can choose whether or not they want to build a private or public dApp, and the users can choose whether or not to interact with a public or private dApp. So in the system, we have two different Merkle trees. We have a public Merkle tree, and we also have a private updatable Merkle tree. And this is different to some other teams using nullifier sets and decoupling the spending of private inputs and outputs. So in an example here, if you interact in the Ola ecosystem, we use UTXOs under the hood, by the way, just as many other privacy teams. If you imagine that Alice wants to pay Bob, then to the far left here, it's very small, but it says Ola. Then if you would want to pay Bob, and Bob would be what says CM0 here, that stands for commitment, which is basically plain text encrypted data. In that transaction, the only thing that would be visible would be the sender, so that would be Alice. Now, if Bob wishes to make a payment to whomever, now everything's fully private. The one thing that we've made an addition here is the traceability. So the UTXOs, or rather the encrypted plain text data, the commitments, they are linked to each other. Now, this is really a spectrum of trade-offs. So you're lowering your privacy compared to some other solutions where everything's hidden because you can trace the UTXOs, or the encrypted data, but you're also increasing the compliancy of the system. You no longer have this complete black box where you have no clue to what's happening, and if you go into the system and out of the system, you could basically just wash money. So should we realize down the line here, let's say 1,000 transactions later, that the originator Alice wasn't actually Alice, that was a criminal, then we can help and pinpoint to where the funds have gone and maybe when they exited. You could also further, in theory, improve this by having some kind of DAO mechanisms where you can, if you provide enough proof or evidence that somebody might be a bad actor, you could freeze their funds and so on. So we're looking to build a solution where we can bridge the gap between the Web 2 world and the Web 3 world, where it's acceptable by governments to have these kind of solutions, but we're not compromising that vital end user privacy. So we want to preserve that privacy for the end user. Right, so where are we right now? We launched our POC earlier this year, and we're looking to launch our dev testnet. So at the moment, what you can do on the machine is basically you can run the virtual machine locally on your computer. You can run a simple smart contract, and you can generate a proof for that. What we're looking to do now is to launch our dev testnet coming next month. And then we'll have our nodes operating, meaning the node will take care of the proving and also the verification for you. And you can request that verification back to your local machine. And then a final step would be to have a public testnet where the verifier would sit on top of some kind of test network, like on Ethereum on Sepolia, as an example given. So by the way, if you're interested to come and work with us, we are actively right now on our socials. We have a link. I think I have a QR code for this that you can scan if you want to get allow listed to either deploy some kind of dApp and try the system out, or if you want to try and run a node with us. Right, so everything that we do is open source. So you'll find all the code in our GitHub. One thing that I forgot to mention in the beginning is some of the levels of abstraction that we're doing. So I never mentioned what language we're using. We have our own language called Ola Lang, or Olang, and it's basically a Rust fork. So if you are familiar with Rust, you're going to be good to go. It's Rust with the Solidity types. So if you're familiar with Solidity and Rust, you're going to be having an easy time. We're also looking to add kind of high levels of abstraction here. We know that coming in and writing CK dApps isn't easy, so there's no CK DSL components in our language. It's just basically Rust. So there's no need to deal with any circuit writing at all. We have constraints on the VM itself, so the VM will generate any circuit for whatever arbitrary code you want to deploy on it. And yeah, that was it. So I'll leave this up for a second here, and you can scan the QR code, and happy to take any questions. Yeah, don't be shy. One at a time. No? Over here?
Polygon ZKVM is using Starks just because it's fast, but there's no privacy. And then they're taking the Stark proof and making a Snark proof out of it for sickness. And that's how they work. If you are not using Starks, if you're not using anything that fast, isn't this going to be computationally kind of slower and maybe not competitive on the market?
So in terms of CK efficiency, we've done a lot of research on this, and we've actually pivoted many times. In the beginning, we weren't looking at Starks at all, and then new research came out. We're continuously looking at the best CK option. We looked into incrementally verifiable, well, that's a mouthful, verifiable computation as well, and we can add that as well if we want to. I think all products that are on the market today use some kind of snark at the end of the chain. Even if they're Stark-based, they use a snark. And I think that might be the route or the path we're going down as well, at least we see some breakthrough. But yes, you're altering the security premises then. And I think even Diego from Lambda class said this before, that, I mean, okay, you're losing the quantum resistance, but sure, I mean, the EVM and Ethereum itself is based on elliptic curves, so you need to change out Ethereum in that example as well then. Yeah. Any other questions?
How does Ola compare to like other ZK-friendly like like VMs, for example, the Cairo VM itself in terms of throughput, like as an execution, from an executional perspective, like, so have you like done some benchmarks and compared it with Cairo VM or other ZK-friendly VMs? Mm-hmm.
Yeah, sure. So there are some benchmarks on the GitHub repository that you'll find. We have some benchmarks for a Fibonacci sequence. I think we ran that like 1,000 times to, I don't remember to exactly what number in the sequence, but you'll find that on the GitHub. We also actually, mentioning Starkware and Cairo, we also run algebraic risk. We're a risk-based solution, which has taken inspiration from Starkware specifically. We also have some other tips and tricks I didn't mention because in the mean of time here, but we're using, if you're familiar with Starkware and hints, we have a similar concept. It's called the profit in our solution, and that's basically just about taking, instead of proving something natively in the VM itself that's going to be included in the trace, an example given could be the calculation of a square root. Now, doing that natively requires quite a lot of opcodes. So what you could do is you could run like a Python script outside of the VM. It's actually handled by the VM as well. So when I say outside, don't think outside, but the VM could run a Python script, get the result for that calculation of a square root, and then we can just assert it with 2 or 3 opcodes that the result we're getting back is correct. So there's many like tips and tricks and tweaks we're making to make this as CK efficient as possible. One last question. I think we have 10 seconds, but maybe the panelists aren't ready anyways.
Since you mentioned your UTXO with privacy enable, which we have a competitor which I heard of is Alio, so I'd just like to hear from your perspective of your differences compared to Alio and what are your advantages too.
Yeah, so first of all, I think the Alio team they're doing great work, and we're actually good friends with the Alio team. One difference, language level. So for developers, they have a CK DSL, so you need to learn about. So basically, the problem, right? The problem is we have developers here, and they aren't familiar with writing CK dApps. Okay, so how can we lower this threshold? Well, how they went about it is they're taking the circuit components, and they're shoving that into the language as templates for the devs to use, basically, in Leo. So that's a difference in Ola. So instead of taking these circuit components and shoving them into the language, we're taking them and shoving them under the hood into the Ola VM itself. So we put constraints on the VM, and you basically just have your high-level language, and that will compile into whatever circuit you need. So you don't need to deal with any circuit writing into the language itself. So that is one difference. Then another difference is in terms of the Merkle tree structure we were talking about. So we have less overhead in managing fewer trees. And then we have the trade-off, privacy levels. So if you can link encrypted data, that shrinks your privacy by a little, but it increases the compliance quite a lot. So in a fully decentralized world, we think in our team that this is the best way to go. In a hybrid world where you maybe interact with Sexes and other centralized solutions, you could maybe put requirements to, well, you must show your viewing key to ever deposit into this central exchange. A viewing key, by the way, for those who don't know, is a non-enforceable key that relates to your private inputs, but I can't force anybody to reveal their key. They must do that themselves. So there are some complications by doing or going down that route. So these are, yes, some of the few differences between the Aleo team and ours. On a CK stack viewpoint, they're running sexy as their protocol, right? So that's different to us. So there are differences here and there in terms of, the two systems. Yep. Should we, any last? Do we have time? One more question, one final question, or are we good? Everybody's going to build an Ola and go onto GitHub and pull the repo? Yeah. Yeah, so thank you so much. Please try it out. It's super simple. And if you are a developer looking to try something new, happily working with other dev teams, so we'd love to see more traction. So reach out to me. I'll be around here. Yes, come and say hi. And thanks to Ingo Nyama and also Geometry and Lambda class for helping out with the organization. Yeah, thanks.